All right, hello. We are back with another Leetcode question. Well, it's technically still Leetcode, but like this is the classic dynamic programming question, the 0 1 knapsack problem. Um, so let's read the example. We'll read the problem statement and we'll get into it. So, given the weights and profits of n items, we are asked to put these items in a knapsack with a capacity C. The goal is to get the maximum profit out of the knapsack items. Each item can only be selected once, and we don't have multiple quantities of any item. Let's take Mary's example, who wants to carry some fruits in the knapsack to get maximum profit. Here are the weights and profits of the fruits. The names actually don't really matter. It's only important for this example part because we don't actually have names. But yeah, so the weights are 2, 3, 1, and 4. Profits are 4, 5, 3, and 7. Our knapsack capacity is 5. So given these examples, our best profit is a banana and melon, which doesn't go over the total weight, and we get the most profit at 10. So problem statement is given two integer arrays to represent the weights and profits of n items. We need to find the subset of these items which will give us the maximum profit such that the cumulative weight is not more than a given number C. Each item can only be selected once, which means we can either put an item in the knapsack or we can skip it. So we can just get into implementing solutions. So we're going to be doing the length of profits as a variable n, because we will be using this variable a good amount of times. Well, I mean, it's okay, but just to save the computer from having to do it, because I don't know if it's the cheapest uh, method to call, but yeah. So now we're going to create a 2D array uh, where we will be capacity plus 1, where we will be storing our memoized solutions. So basically, we're doing bottom up dynamic programming, which means we're going to be building every possible solution, and at the very end, we will have the solution of the of our ideal situation in a sense. Um, so here we'll be building an array that's capacity plus 1, width long, and then so this is the number of columns and this is the number of rows. So for every fruit plus 1, and for all the capacities, because since everything is zero based indexing, we'll have up to our actual capacities amount in our array. And so here we're going to be doing for I in range of 1 to n plus 1, and for j in range of 1 to capacity plus 1, we're going to be doing one of two things depending on this first condition. If weights I minus 1 is less than or equal to j, then we'll be doing dp of I j is equal to the max of dp I minus 1 j, or dp of I minus 1 j minus weights of I minus 1 plus profits of I minus 1. And then if it's not less than j, then we're automatically just going to set it equal to dp of I minus 1 and j. And at the very end, we're just going to return dp of can't type capacity. There we go. So basically, we're going to be using previously built solutions to build onto our current solution, right? So here I'll type out the array that I had earlier. So basically, we're creating we're looking at, all of these are the same, but we'll just focus on this one. So we have a capacity of 5, so we want 6 zeros, right? And then we have 4 fruits, so we want 5. So we have a 5 by 6 array now, right? And then actually, let me put in one more, and then let me put in another column for our capacity. So it's 0, 1, 2, 3, 4, 5, right? And then this is fruit 0, essentially 1, 2, 3, 4. because so we're going to have like this empty row basically for fruit 0, and we're always going to have 0 profit because we're not looking at any fruits, right? And then for 0 capacity, we're always going to have 0 here. So we're really just building on like these 5, and the 4 rows below it, right? So basically, we can actually just run through this because we're going from 1 to n plus 1 and then 1 to capacity plus 1, right? Since we don't actually hit this because this is exclusive, this is how we're establishing this like 4 by 5 bound. So at a weight of 1, like for fruit 1, at a weight of 1, since fruit 1, the weight is less than or equal to j, we take, basically you go up 1 row and you subtract the weight. So it's 0 plus the profit, which is 1, right? And so I'll just save us the time and just run through, because looking at fruit 1, regardless of what the capacity is, we can only have a profit of 1 because our weight is just 1, right? So now we go to the second fruit. And so at weight 1, we can't do anything because the weight is greater than j, which is our current capacity. So we just take whatever is in the last row, or like the row above it, so it's 1. And now we have hit this condition where it's equal to. So I'll just save us the math, but if you go up 1 row and subtract the weight of the fruit, which is our current fruit, which is 2, we get 0 plus the weight plus the profit, which is 6 actually. Whoops, that's a mistake. And then so at a weight of 3, we do you go up 1 row and then minus the weight of our current fruit, which is 2, so we go 1. So it's 6 plus 1, which gives us 7. And to save us the rest of the math, because it's going to be the same anyways, it's 7 and 7, right? And so if we go down here, this is going to be the same, because for weight of 1, we're always going to have 1. So I guess I can also change this as well. Like, this isn't how the computer runs it, but like this is how we're filling in the array, right? And so here, for a weight of 2, it's still less than our current weight, which is 3. So we just take the value from above, 6. Now we're at a weight of 3, right? And it's equal to, so then we'll take the highest weight between the weight of, like, if we go up and minus 3, which is 0, plus 10. So it'd be like 10, or, the value above, which is 7, but 10 is greater than 7, so we have that here. It's going to be slightly off, but, we'll deal with it. So now for a weight of 4, you go up and minus 3, so you get 11, right? And then for a weight of 5, you go up and minus 3, so you get 2, and you can get 16 here, right? So that's how our array is now. And so for 4, the weight is 5, so everything before 5 will just be whatever's above it. So 6, 10, 11, and then here we get the maximum of what's above it, 16, or whatever the fruit we're currently looking at is. So it's also 16, so that doesn't really matter, right? So we have 16 in both, so our answer here is actually 16. And so instead of running through it again, we'll just see what we're expecting for these other two problems, which are the same profit and weights, right? For weight of 6, you can get a 5 and a 1, which should yield you 17. And, whoops. And then here, let me put another enter here. 7, you can get a 5 and 2, which is 6 plus 16, which yields 22. So that's our expected result. If we were to run the Python file, we get 16, 17, and 22, which are our expected results. Let me move that up a little bit. And yeah, so that's how you do the 0-1 knapsack problem. And that's the code for it. And this is doing bottom up dynamic programming, by the way, because there's also top down. Bottom up is more comfortable for me, but I mean, maybe some problems top down might be easier, but for this one, bottom up is just easier for me to comprehend. So yeah, that's how I would do this problem. And yeah, thanks for watching.